Today, we are incredibly honored to have two distinguished guests with us. We are joined by Professor Chang Liu, Assistant Professor at Peking University. And we also have the great privilege of welcoming Professor Angela Schoellig from Technology University of Munich. Hi, Professor Schoellig. Hi, Professor Liu.
Hello, hi.
Hi, it's fantastic to have you two with us today. We are looking forward to your valuable insights on this fascinating topic. Now, I would like to hand over to Professor Chang Liu to begin today's academic discussion.
Okay, great. So hello, everyone. My name is Chang Liu from Peking University. So today I'm very happy to be here as the moderator for this webinar. This is actually a pre-workshop webinar. My colleagues and I are actually organizing a workshop named this MICROI, multi-agent cooperative systems, and swarm robotics in the era of generative AI. Actually, many of you may be wondering, why do we need this workshop? Well, the main reason is because nowadays the generative AI has already made significant progresses in robotic navigation and manipulation. However, its application to multi-agent systems still lags behind. So we believe this is the right moment to open discussions on multi-agent systems and swarm robotics in the era of generative AI. And today we are very delighted to have Professor Angela Schoellig with us. So I believe actually many of you already know Professor Angela, but still let me take a moment to introduce her once more. Professor Angela Schoellig is a professor of robotics and AI at the Technical University of Munich. Her research combines robotics, controls, and machine learning to improve robot performance, safety, and autonomy through experience-based learning. Among many honors Professor Angela Schoellig has received, some of them include the NSERC McDonald Fellowship, RSS Early Career Spotlight Award, and a Sloan Fellowship. She was also named an innovator under 35 by the MIT Technology Review, and she has led her team to 4 wins in the SAE Auto Drive Challenge. Professor Angela Schoellig earned her PhD at ETH Zurich and holds master's degrees from Stuttgart and Georgia Tech. Okay, so next I would like to hand over the stage to Professor Angela Schoellig, who will deliver a talk titled Areas Formed from Safe Motion Planning to Language-Based Interaction.
Thank you so much. Let me share my screen. Welcome, everybody. My name is Angela Schoellig, and today I'm talking about safe motion planning and how it enables the deployment of learning and generative AI in aerial swarms. But first, I'd like to also do a small update for you. A lot of the work I'm presenting today was also driven by Dr. Siki Su, and she will be joining the School of Computing Science as an assistant professor School of Computing Science at Simon Fraser University in Vancouver as an assistant professor. So please also follow her next steps as she continues to drive her scientific career. So aerial robot swarms have captured our imagination for a long time, from visions of autonomous environmental monitoring, infrastructure inspection, to large-scale artistic performances, such as the drone light show we recently saw, which was a new Guinness World Record with more than 10,000 drones in the air. But to move from this vision to reality, we need methods that are safe, scalable, and ideally intuitive for non-experts to use. And while we have seen that robotics has made huge progress by learning from robot-specific data, this is usually carefully collected demonstrations, experiments, and simulations, it is more difficult to expand this beyond. But let me show you a few examples where we learn from robot-specific data and show how data collected from robots can improve their performance without jeopardizing the safety. So here you see the green line much better tracks the red line, and that is just because of learning from a few minutes of real flight data. And we can here reduce the error by 59%. We also have a recent work where we learn from robot-specific data, real-world experiment data, and this is presented at IROS this year. So here we show that we can improve state-of-the-art drone racing performance by learning from a few trials of real flight in the arena. And one more example that was at ICRA this year, so May 2025, is where we showed that yes, we can safely learn with flying vehicles if we use, for example, a safety filter while training the reinforcement learning agent. So here you see we don't have constraint violations, the red line, during the training with reinforcement learning, which generally can cause constraint violations. But with this safety framework, we avoid constraint violations, and we also show by not trying out unsafe actions, we actually converge faster and get better performance with less data, which is again the red line. And so if you want to learn more about this work, I encourage you to look at the RAL paper that is cited here at the bottom. We have also worked on this for quite some time, and in 2022 summarized the state-of-the-art in safe learning in robotics in a survey paper in the annual reviews journal. But while learning from robot-specific data has driven impressive advances in control and autonomy, it still limits us to what a single robot or lab can provide. And we all know that generative AI offers access to internet-scale knowledge and enables things like image understanding and open-world image understanding and intuitive interactions through language. And so the challenge, and maybe also the opportunity, is how do we integrate the richness and the creativity and the world knowledge of generative AI into robot systems such as aerial swarms that require performance and safety. So how do we bring these two together? And so the main message of my talk today is that by enabling or using safe motion planning, we are able to deploy learning in generative AI in a safe manner in aerial robotics and specifically for aerial swarms. And you can view this also like this. So we leverage models and prior knowledge for a safe, efficient, and scalable motion planning. And then we leverage data-based inference and reasoning to improve performance, capability, and intuitive interaction. So really the two combined provide a much richer way to operate aerial swarms. And so in this talk today, I'll share our recent efforts along 3 complementary directions that bring this vision closer to us. And the part 1 is the model-based, safe and efficient swarm coordination, where we really guarantee we keep aerial swarms safe in the air. And then part 2 is how we recently programmed aerial swarms through language, enable non-experts to interact with aerial swarms. And part 3 is kind of the foundation for many of these, a lot of this progress, namely open source simulators and data sets that we have provided to the community and that we encourage you to use and contribute and collaborate with us on, such that we drive progress further in the future. But this talk is also a story that kind of is a personal story, because it started in 2009 with a one-vehicle dance performance to music. So this talk is also about a story from a performance like this. It seems now very primitive. That's why we move in the club, and it's all right. That's why we to a performance like this, where we programmed 20 drones through language in minutes.
They'll be calling me, they'll be calling me royalty. Best to give me loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty.
Let me start with part one, which is critical to kind of make the performance that I just showed you possible. And that is safe and efficient swarm coordination. And what we mean with this is maybe summarized best in a video like this. So here, each drone has a target destination to go to, and we want to plan motions that are feasible, executable by the drone, and those motions avoid collisions. So each drone has a target location. Here is randomly assigned, and now they coordinate their motion to safely reach their goal. And this is really the problem we have been trying to solve, and is underlying a lot of the performances that I show you later in the talk. And this is something we have been working on for quite some time, always in the context of dance performances or performances to music, but of course the impact is much broader. And just to show you what can happen within like 12 years. So we started, and that was a highly cited work, as it was very novel at the time, where we had an offline centralized planner that coordinates the motions of all drones together. But there the computation time scaled exponentially, and we kind of got it down to 0.3 seconds for 5 vehicles. But that's not enough to, for example, do real-time adaptations of the vehicle plans. And then the next work was an offline decentralized planner, and that achieved a 85% computation reduction and run times of smaller than 2 seconds for 25 drones. So when we kind of planned these type of transition motions for 25 drones, it took less than 2 seconds. Still quite some time. And as we progressed, we leveraged additional online decentralized approaches and got down to 50 milliseconds for 20 quadrotors, and also improved the performance of the transition time. So drones could reach their goals faster because the method was less conservative. And finally, we did one more step in reducing the conservatism and making it computationally more feasible, where we improved success rates, reduced the mission times, meaning we were more optimal and faster for drones to get swarms of drones to go from A to B. So 36% reduction in mission times, and again, 42 times faster per agent computation time. So this was really a journey where we built on top of previous work and slowly really significantly improved the scalability of these approaches. And to show you kind of what is behind the best performing method right now, I start with the offline centralized approach, because this was really, the starting point. So the offline centralized planner formulated the problem as a joint optimization problem for all quadrotors together. And then the optimization variable were the acceleration of each drone. And the planning was done by minimizing the energy of all drones subject to the vehicle dynamics. So we want to make sure the motions we plan are actually doable for the vehicles. We had position, velocity, and acceleration and jerk limits, so actuation constraints basically, and collision avoidance constraints, of course. And those collision avoidance constraints are non-convex, so the whole optimization problem is a nonlinear optimization problem, and you can solve it with sequential convex programming, which approximates this non-convex nonlinear optimization problem by a quadratic cost function and linear constraints. And so the result you see here at the bottom in these pictures So when these 5 drones need to change their position, these were the motions our motion planner would plan to avoid collisions. But one important thing is when you do sequential convex programming, you approximate the free space, which is here in purple, which is a non-convex space, into something linear, a linear boundary. And therefore, you highly restrict the free space of drones and make it more difficult to solve this coordination problem because each drone has less space to move around. But this led us to performances such as this, where you see many of these transition motions in this kind of dance performance. So you, for example, see a transition motion now. And also now when they go in a new configuration. At the time even to do these dance performances. However, they were all hand designed, right? But this was our offline decentralized approach. And offline centralized approach, sorry, there's a typo. And then we improved the scalability to scale to larger swarms of drones by computing something in a distributed manner. So this can still be on one computer, but each drone solving their own optimization problem now. And how is this done? So basically, each drone computes their inputs to their goal location, where they have to go. And then they share the predictions with their neighbors to avoid conflicts later. And then they execute, so they share, then they apply the first input, and then they repeat and recompute again. So each drone solves their own optimization problem, and the only thing they take into account is the predictions of their neighbors to avoid conflict. And when you do this, then you get already significant improvements. So here you see the success rate. So do the drones reach their target without collisions? And the new method, this distributed model predictive control method in red, has very high success probability compared to the centralized approach, which of course is has less approximations. And the fully decoupled means that each drone just solves their own approach without taking into account that there are other drones in the space. And so we are as good as the centralized approach, basically, but with significant lower computation time, if you look at the red line compared to the blue line here. And the suboptimality by making this approximation of each drone solving their own problem is not that bad. So we still have a good travel distance. So the drones arrive at the target or at their goal position at the same time as in the decentralized approach. But this allowed us to, for example, online recompute relatively quickly when something in the space changed or something in the plan changed. So now 2 PhDs just move the drones to a random position, and our decentralized model predictive control approach can quickly recompute the motion. From that, we went on and improved it further to reduce the conservatism in the approximation of the non-convex free space. And the key idea here is, and more details are in the paper you see here at the bottom called AMSwarm, is that we do not do any approximations and still obtain a quadratic program which is very efficient to solve. And how is this done? The core idea is that we use a polar reformulation of the non-convex quadratic constraints and then apply an alternating minimization approach. And this leads to subproblems that are convex quadratic programs and have a closed form solution. So you see here, we basically approximate this, the free space through an angle, or parameterize it through an angle and a distance, and then use that to push here the colliding trajectory outside of the collision area around the obstacle. And this really significantly again improved the performance. So here in blue and in yellow are our two approaches with slightly different variations, but you see blue and yellow have very good success rates still with increasing number of agents. So if the success rate is below 100%, it means it doesn't find a feasible solution that allows all agents to travel to their goal without collision. So if it's too dense and too many drones in too little space, sometimes there's no way you can find solutions, but still up to 50 drones, it was still pretty good in a relatively narrow space. So always the drone density matters. And then the computation time was very low compared to our previous best approaches in green and red. And also the mission time, so the optimality of the trajectories was better than our previous approach, actually. Even so we have lower computation time and better trajectories. And so then we could really do real-time interaction with known moving obstacles, where the drones in real time recompute their coordinated motions based on an unknown moving obstacle. Yeah, so this is really where we are at. So they can even react to real-time disturbances or changes or moving obstacles. And so this was kind of the trajectory on our coordinated motion planner for aerial swarms that builds the backbone for what we did next, namely programming robots through language. And so I had been working on drone motions that are synchronized to music for some time, but there we always hand designed the motions to the music, right, manually. And so we had motion primitives that were parameterized, and we designed those as experts, and it took us multiple hours to design a new choreography for a new song. And here the idea was, can we use large language models to facilitate choreography design through language? And for me, this is also just a proxy for a lot more interesting problems in robotics, where we want to enable non-experts to interact with robots through language. And we did some first tests. For example, testing, can a large language model understand rough geometry? And here you see, for example, generated motions and waypoints from an LLM if you tell it to move a swarm of drones in circles, along lines, towards the center, or they should orbit around. And so there is some basic understanding to translate qualitative instructions into 3D motions. But the difficulty is, of course, the large language model, especially vanilla large language models such as ChatGPT, they have absolutely no knowledge about the dynamics of the drones, the physical capabilities, the actuation limits, etc. And so collisions could easily happen with these generated motions from a large language model. And here the large language model can provide just waypoints for each drone or parameters of motion primitives. And so the idea is really to combine the design capabilities and creative capabilities of large language models with the safety filter, our safe motion planner that I just showed you in the first part of the talk. And the safe motion planner, it encodes core fundamental, collision constraints, as you saw, but also the physical capabilities of the drones. And so what the safety filter would do is it minimally modifies, so we get these motions that are generated by the large language model. And the idea is let the motion planner minimally modify the trajectories to guarantee feasibility and safety. And so the overall block diagram looks like this. So we start with an audio file, and there's some music pre-processing, which is very standard to get the beat times and the audio features of a song. Those are provided to the large language model, so the language-based choreographer, together with the song name, the genre, and some desired behavior we want to see. And then the language-based choreographer provides either motion primitive names and parameters or simply waypoints. And those go to a motion primitive generator. And we get raw trajectories, and they are translated into certified, safe, feasible trajectories by our optimization-based safety filter, so the first part of the talk. And then we can test and see those trajectories either in simulation or right away in the real world. And we can look at the visualization of the robot performance, and if we like it, we can keep it like this, but we can also, as a non-expert user, interact with our language-based choreographer and, for example, give reprompts in natural language, such as, please fly faster, I want the drones to be further apart, I want the drones to fly higher in the space, do more circle motions. You basically can use natural language. You don't need to instruct the user at all what to say. And the language-based choreographer, again, designs a choreography that is then made safe by our optimization-based safety filter, our motion planner, and then we can see it again in simulation or in the real world. And so what we see then is when we look at what the large language model generates without the safety filter, we get inter-agent distances, which is here on the x-axis, that are sometimes way too close and generate collisions. So everything that's smaller than this red line, the vertical red line, is a collision between the two drones because they are too close together. And so without the safety filter, of course, it's understandable. The large language model knows nothing about the drone's size, for example. It generates motions that are clearly unsafe. But then when we pass them through the safety filter, we minimally modify them to make them safe. And you see all of them are then safe. And the safety filter ensures that the inter-agent distance is larger than the safety threshold. We also have additional analysis that shows that motion is generally aligned with the beat times and also with the amplitude of the songs. So we did an analysis with respect to different songs. We also looked at how we can further improve the success rate if we have many drones. And here we went all the way to 200 drones. So designing choreographies using a large language model for 200 drones. And we show that if we allow the large language model to also choose from motion primitives, such as circles, spirals, wave motions, and we allow it to do self-corrections, meaning our safety filter can automatically report back that the design was not successful, and it cannot modify the trajectories to make them safe. And then the large language model automatically redesigns those motions. We can actually get very good success rates all the way up to 200 drones and more. And so if you are interested how this looks like, this is the type of interaction you would have. This is really the type of message you would write. And then the output would be maybe, in a worst case, maybe a design that is okay, but pretty boring. Then you can re-prompt it. And again, you can reprompt again. And then if you're happy, you can basically deploy it right on the drones. And here are a few examples, right? For example, here is left the original one without any reprompt. And on the right, there's a reprompt with using less circles, please. And you see the difference. And here's another example again.
And on we'll
simulator really capable. And so this is in simulation because we don't have 100 drones ready to deploy. But we can simulate up to 100, design and simulate up to 100 drones and more by making also our simulator much more efficient. And so this is my third part and last part, and also something I encourage you to do is we really scaled up significantly by using and developing our own open source simulators and data sets. And we also at some point actually analyze the impact of releasing code with your publications. And here you see the colored kind of lines are publications that had released code with them. And after 6 years, the publications with code had significantly more citations than without. And that was true across NeurIPS and the ICRA conference. So really releasing code with your publications can really help democratize progress. And I just want to highlight two that may be interesting for people here. One is gym-pybullet-drones. This is a bit of an older simulation environment that we built specifically for aerial swarms and enabling the interface to typical RL libraries, such as stable baselines and others. So this was really meant for multi-agent reinforcement learning in simulation before translating this to the real world. That even went so far that we use this in competitions as well as in our courses. And yeah, I encourage you to have a look. And our very latest work, which we have not talked about, but the code is available on GitHub, is Crazyflow. This is behind the hundreds of drones that you saw in the simulation for our dance performances, but we also use it for courses and racing. And it's a fast parallelizable drone simulator with checks. And so if you are interested in this, this is really what builds the backbone of what we do right now. And it has models of the Crazyflow, so the open source hardware platform from BitCraze, but of course you could also add your own physics model of the drone into the simulator. But if you work with Crazyflow variations and variations of those, you could directly use the simulator for doing reinforcement learning simulations before going to the real world and deploying it on the Crazyflow. There's also a few other open source tools that you may find interesting, from safe controlled gym to an ultra wideband indoor localization data sets for drones. So if you are interested, have a look at our open source repositories. Also AMSwarm, the safe motion planning approach in its core version was open sourced. So what have we learned about deploying robot swarms in the real world? What I showed you is that for collision from motion planning of swarms of drones, we really went from centralized offline methods that had computation times of 0.3 seconds for 5 vehicles to decentralized online methods that have milliseconds per agent computation times for 60 and more drones. And we went in terms of the choreography design. For swarms of drones, we went from manually designed choreographies that took hours for 6 vehicles to manually design by an expert to design times of minutes for hundreds of drones by a non-expert. And all of this was also enabled by open source tools that we have developed to further facilitate collective innovation and also make our research reproducible. So finally, what is next? What are we looking at? So a few ideas we are following right now is, on the one hand, how can we do even tighter coupling between machine learning and model-based methods to really get improved performance, safety, capability, and scaling. But we also have several works to integrate perception into the closed loop for real-world autonomy, which of course is a very important part. And finally, something that I'm very excited about is also how we can embed semantic understanding in the decision-making. So if you go back to the initial examples I showed you about environmental monitoring or inspection, a semantic image understanding of what the robot sees could enable it to automatically inspect without an expert to design waypoints to go to, right? So translating Gen AI to other application fields beyond drone performances. And so ultimately, we try to bridge what robot-specific data can tell us about robots and how internet-scale knowledge gives us the breadth of information and the creativity and the possibility to design systems that interact with non-experts. And so all of this is towards kind of safe, scalable, and interactive aerial swarms. So I'm happy to conclude here and answer your questions. And if you want to see more of our work, you can visit our webpage. Thank you.
All right, thank you so much, Professor Angela. I think this is a very wonderful presentation. I'm very impressed by the journey from the centralized offline planning of a few agents to the current decentralized online planning of swarms. Yeah, this is awesome. And I do have a very quick question. So actually, in your last work, where we use large language models for the dancing of the swarms, do you reprogram the prompts to fine-tune the large language models, or do you actually retrain the large language model?
No, right now we really use vanilla large language models, and the only thing is we provide context with an initial prompt. For example, roughly specifying the space the drones have available, the number of drones, maybe a bit more about the music, what type of song it is, but we do not fine-tune right now. Yeah.
Gotcha.
The only thing we
Thanks.
do is automatic reprompting. Yes.
Yeah, that's still also very fantastic. Great. Yeah, so actually, we have actually collected some questions like before from the registration. I have compiled them into 3 categories. So I think it's I'd like to discuss with you about the 3 questions. Let me first share my screen. Can you see my screen?
Yes.
Okay, cool. So I think the first question is actually because okay, let me see. Yeah, so the first question is actually because we know that like nowadays the robotics communities has made very like incredible strides in the single robot systems. like particularly with the large scale data and the foundation models. But there is like a relative lack of focus on multi-robot system. Of course, your work is one of the pioneering work in this area, but from a more general point of view, do you think the lack of focus on applying like generative AI techniques to multi-agent systems is only because we are still solving some foundational like problems for single robots, or do you think there are some more like fundamental bottlenecks that prevents us from directly applying like generative AI techniques to multi-agent systems?
Yeah, that's an interesting question. So I think on the one hand, right, if you just naively apply, let's say, foundation models to multi-agent systems, it really scales very badly in terms of the amount of data you need, depending on the size of the swarm, right? If you have 100 drones, let's say, and you want to do just end-to-end learning, let's say, from the vision inputs of each individual drone to a coordinated performance, I think this just scales so badly with the amount of data you need that this is currently impossible. But if you do, I think we need more clever methods then. But it can start by saying, each drone is already in its own the same. So we have a homogeneous swarm, and we take that prior information into account. We could use approaches more like graph neural networks or graph-based methods, where we kind of take in, somehow provide the foundation models with more prior understanding and background, such that those are data efficient. And then, of course, with multi-agent systems, even more safety is critical, right? Because collisions can easily happen. I think we see some first work with bimanual manipulation, where, of course, also two systems more or less collaborate. But for drones, we would want to scale this up way beyond just two drones. So I think we need more prior inductive biases.
Yeah, that's what makes sense. So do you think we have like benchmarks for evaluating a multi-agent system right now? Because we know we have a lot of like benchmarks for single agent systems.
I'm not aware of many. Yeah, that's probably also a problem, right? I'm not aware of many, and some are simply in simulation. So I hope also that our Crazyflow simulator, plus its ability to then do sim to real on an open source hardware platform, the Crazyflow, enables people to more think about different benchmarks. Yeah.
Mm-hmm. Cool. Thank you. Okay, so the second question is actually when we actually like consider extending like existing like architectures such as vision language action models or the diffusion policies to multi-agent systems, what do you see as the primary challenge? Because VLA and diffusion has been very popular for like manipulators or other single agent systems.
Yeah, I think that this goes back a bit to my answer to the first question, that we really need to think about what are the suitable architectures, and I don't believe the current ones are well suited yet, unless we have huge amounts of data of a multi-agent system, which maybe we can generate from a simulation environment, but nevertheless, it's still magnitudes of more input-output data that we need and scenarios that we need compared to a single agent. And so I think we need better also really think about the fundamental questions and better fundamental architectures that somehow embed knowledge that we have that this is a multi-agent system with maybe agents all having the same capabilities, etc.
Yeah, thanks. That totally makes sense. And I think the last question is actually about the future research, because in the audience, I believe there are many students interested in the area of multi-agent systems. So what do you see as the key future research directions for multi-agent systems? Of course, you have listed many in your presentation, from a broader point of view, what do you view as the very critical research directions?
Yeah, I mean, overall, I think there's not a lack of open questions and directions, even with providing very reliable hardware. It is still, I think, something that we can further improve. Right? On the other hand, there's companies such as Amazon that have shown that they can operate millions of robots at the same time with, very good, probably hardware reliability. But in terms of one of the future directions I really see is that multi-agent systems can be operated and interacted with by non-experts. And I think this goes beyond the applications that I showed, to go a bit more in depth in terms of what I mentioned in my talk. I mean, for environmental monitoring, for example, if I want to monitor a more complex area, I have to still manually put a lot of information into the system to make the drone fly well and capture the images I need, such that all the images have enough maybe overlap, and I can generate the appropriate map. And I need to define some boundaries and define GPS waypoints. And if all of that would be more automatic, I think that would be great. And that vision language models could really help to interact with the system, maybe also just in language define, oh, I see something abnormal in this area, just have a closer look. Right? If I could interact with this in language, this would be really amazing. Or if I monitor or inspect an infrastructure, I just say, this is the building I want to inspect, go ahead. And I don't have to define GPS waypoints, these kind of things. I think this is where vision language models are at a higher level. And the low-level motion planning and control is still very standard. And then guarantees the low-level performance and safety. And so these kind of things, I think, are really on the horizon and are very exciting for applications with multi-agent systems.
Thank you so much. Yeah, as mentioned, we do see a very bright future for applying large language models or vision language action models into multi-agent systems. So I think those are three main questions from the registration, but we do have some live questions online. So I also like to discuss them with you. So one question is actually about the dancing demo you have shown. So the question is, Professor Schoellig, could you explain a little bit more about the communication with neighbors, and especially what happens with this information? Would there be maybe a wave if one drone is in the way of the other and in the way of the next and so on? So will there be some wave in this experiment?
Yeah. So first of all, I have to say, right, for these dance performances, there's still a single computer that commands the whole swarm of the drones. And so there's no drone-to-drone communication in what I have shown you. So what happens is then for the indoor experiments, we have an overhead camera system that provides us with the positions of all drones. And then we can make real-time adjustments if we want to avoid collisions, if there's an unusual behavior. But there's no direct drone-to-drone communication. This is all still centralized. When I talk about a distributed implementation of the motion planner, it still means that this can run in multiple threads on just a single computer. It could run on a cluster, but you don't even need that, right? It just means we have individual optimization problems that we solve, and these optimization problems exchange information only at the beginning and at the end. So we don't solve one kind of big optimization problems for all drones, but we solve one for each drone, and there's an information exchange between them. But that's only a virtual distributed approach, right? It's virtual distributed on one single computer. Yeah. So I hope this answers a bit the questions. Yeah.
Yeah, so actually a follow-up question to this is that like actually I think you are using the Crazyflow as the drones. Is this correct?
Yeah, this is correct. Yeah.
Okay, so I think the onboard computation like is very limited for this platform. So probably we cannot do very good online computation, right?
This is correct. Yeah. So we currently use the Crazyflow because, yeah, we do believe that when we then open source our codes and models and simulators, others can more easily use it. And there's also various variations of the Crazyflow, different motors, different sizes that you can do. But of course, you cannot solve an optimization problem easily on board. Yeah, they're very limited.
Mhm. Yeah, that makes sense. Another question is it possible to directly utilize generative AI to obtain control commands for swarm systems?
I would not do this. Right? I mean, there's absolutely no guarantees. I mean, these are highly safety critical systems. And why would you want to? Because we have solved that problem very efficiently and well. And now you would just need to collect a lot of data to solve a problem we have already solved. So I think I don't see as much interest to do this unless you have a real significant application where this is needed, right? Where, yeah, but I don't immediately see it. Maybe once you interact with the environment, and this is how to model ahead of time. But yeah, I think for these applications I show where drones just fly in an open space, I don't see why you would want to do that.
Sure. Yeah, I think even for the single agent systems, people usually also use dual systems. One is for like one utilizes the large language models for kind of slow reasoning, and one use like control method for very reactive, fast control.
Yeah, and maybe I should also be a bit more. Yeah, I think you should at least always question if this is the right way to generate these low-level controls. Like you need a good reason for it. So, for example, right, we in our low-level motion planner, we have a cost function we optimize, and that defines the task. And sometimes these cost functions are difficult to express analytically or difficult to formulate in the first place. So if you have a complex task and this is difficult to formulate, maybe there may be a case where you want to do this directly to control commands. But again, I would always, ask myself the question if it's needed.
That totally makes sense. Yeah. Another question I think is interesting is that it wants to. So the question is how to address hallucination and encourage reasoning among multi-agents. Yeah, because I think hallucination is a major problem in large language model reasoning. Right?
Yeah. I mean, let's maybe go back to our particular application where we design those drone performances to music. I mean, hallucination would be something that it may generate a weird motion configuration that just doesn't look natural to us or is very out of place. But that would not matter too much for us because either we like it and we can safely deploy it, which our safe motion planner can tell us if it's safe or not. And if not, we reprompt, right? So we still have the reprompting scheme. And if the safe motion planner cannot find safe motions in the first place, it can do an automatic reprompting. And so I think hallucination is not a big problem. And I think this is also something you need to think about how to design we know how large language models work. We know their big advantages, but also their limitations, and then how to deal with those. I think basically for us, it doesn't matter in the design as we did it. And that's why anybody can come and provide any type of prompt and it will do a performance in a safe manner. And yeah, So I think especially once you go towards real applications, you need that kind of reliability, right? So you need to be able to deal with hallucinations, either, yeah. And I guess in the design, overall system design, they do not matter for us.
Yeah, I think that makes sense. And I think there are several questions asking the same thing, is that can we, or how can we extend your current work to beyond areas swarm, such as to UGVs or heterogeneous agents or mobile manipulators?
I think the idea easily translates to other areas. Again, what are our assumptions to make this work well? The assumption is that we have a good model of the dynamics and the capabilities and the limitations of the drones. This is part of the motion planner. And that in the motion planner, we can analytically define the tasks through a cost function and then have a high-level instructions. And so I think, for example, UGVs going in a space and you say, please find the backpack for me in some larger space, and they coordinate. I think this is something it could similarly be done in a similar architecture, similar approach, then use a vision language model, maybe. Yeah. If the lower level thing cannot be solved in a very reliable manner, then I think then you need something more complex, and you may need your own robot foundation models or world models. Yeah, but I think there's lots of applications beyond what we are doing. Yeah, I think it's really just a small, very visually appealing and clear example of the capabilities of combining large language models, generative AI with robot swarms. I think you can take this beyond this application easily.
Yeah, of course. Yeah, I totally agree with your argument that the low level or the capability of the platform itself also matters. As long as we can have good controller for those low level control, the upper level decision making part could be easily transferred to other platforms.
Yeah, and I think for other platforms, I think this makes I mean, there's reasons why drones are difficult. They can easily fall out of the sky. But it also is easy in the sense that we are just operating in an open space where we have no obstacles and nothing. So perception doesn't really matter, right? Unless we just need to know where the other drones are. And this is something we control. But once you go to UGVs or something, we also work on crowd navigating robots, then the perception part becomes very relevant. That you embed you need to map the environment, you need to know where the obstacles are. There's also maybe dynamic obstacles and humans around. And then the perception, integrating the perception is critical, which in this work that I showed is not important.
Yeah, gotcha. Okay, so I think this is a very general question. So what would need to be done to specialize large-scale models into collaborative generative AI? And what are some additional key enablers, such as better communication, better computing hardware, or better algorithms?
Oh, wait, let's see if I got the question right. So it was better communication, but to make what is the goal? Making agents better?
Yes. So one question is, what are the key enablers for cooperative multi-agent systems, such as communication, hardware, or better algorithms? That's one question. Yeah, probably you can first respond to this one.
I mean, this is tough to say, right? Because it heavily depends on the application. So we are working also on algorithms with drones where each drone, there's no central computer anymore. So the drones have their own good enough compute, and they communicate to each other, right? And then if you have an application such as this, then of course onboard lightweight, powerful onboard compute is still something you can always have more of. You would always love to have more compute. For processing, you love to have smaller sensors, more lower latency, better bandwidth, communication. And so all of these will be enabler to make the systems ultimately more capable. So I think it's on all levels. It's from hardware to software and AI, where each part can make a big difference.
Yeah, I agree. And the other question is, what needs to be done to specialize large-scale models into collaborative generative AI? I think maybe it's more about like how we combine, like following your work, how can we like continue like using large-scale models, foundation models into the multi-agent systems?
Yeah, so I would say everything we see right now, right? You know, the biggest successes of generative AI is still with relatively simple data sources, which is mostly text. Now, maybe a single image, maybe a video. And then if we see, and this is where it is at right now, and we know how much data is required to train those models. And then if you think about broadly cooperative embodied AI agents, and then the amount of input data, we have multiple sensors on those, they can communicate. It's a whole different set of complexity. I mean, way beyond what we can do right now. And then we need also that similar amount of data. So I think we have, in that sense, at least for the next maybe 2-3 years, far away. I don't know how quickly, so we underestimate how far we can get in medium horizon timeframes. But till then, it is good to think about architectures that help us reduce the information and that we need to process by the AI, or the information we need to communicate between the agents, and leverage underlying tools that we are well aware of, right? Such as state estimation, SLAM, and so on. And so it will be then very interesting what kind of architectures are the most successful. Yeah. But it's an architecture question, I think. Yeah, because we cannot solve the data problem in robotics.
Yes, data is always scarce.
Yeah.
Okay, so another question is, so because you mentioned that in your experiments, the drones relies on the motion capture systems. So the question is, how can we achieve precise distributed control without motion capture?
It depends where. If you are indoors, there's, I think, at least 2 known ways. You could use other types of localization with, for example, ultra-wideband localization, maybe 6G in the future. Or you can go vision-based, that each drone somehow, I mean, if there's a central map, each drone localizes within that central map. There's also some first work for collaborative maps and collaborative localization. So I think, there are other sensing modalities. Overall, they're just not as reliable and precise. I would say none of them are. So that means you need a bit larger distance between the drones, etc. Yeah. And then outdoors, I mean, vision-based, of course, is also outdoors a possibility. You have GPS available, so other sensing possibilities. But yeah, as I said, the perception and the sensing side is something we basically cheat when we do indoors with an overhead camera system. Yeah.
Well, I think because the focus is based on planning and control, right? Not on the perception and state estimation. So that totally makes
Yes,
sense.
for this work, yes. Yeah,
Yeah.
you could, yeah.
Mhm. Okay, yeah. Okay, there's another question. It asks whether you could share the papers that were discussed in this live stream. So I guess like probably we could do this from Amy, maybe from the side, no-code side.
I tried to cite them where the relevant papers on the slides. So I'm also happy to share those slides later. But I think this was also recorded. And then all papers are freely available on archive or our webpage. So if you search for them, you should
Right.
find them. Yeah.
That's great. That's great. Okay, thank you so much. I think that's all the questions raised by the audience. And thank you so much for your great answers and for your insights. I believe it will be very useful to the audience and also to me as well.
Thank you so much.
Cool.
Yeah, I love to stay in touch, and I'm also looking forward to any of the participants and your progress. Yeah.
Thank you. Thank you so much. All right. And then I think, let me see. Okay, cool. Yeah. All right. Thank you so much. And then I think next I will move on to introducing the workshop again. I hinted on this workshop at the beginning, but before I conclude, I also like to draw your attention to the workshop. So this workshop is based on the multi-agent cooperative systems and swarm robotics in the era of generative AI, which actually I think matches very well with what Professor Schoellig just presented. And this workshop is actually accepting paper submissions. The deadline is September 28th, so there's still 1 month from now. And the submission only requires no more than 3 pages, which is actually an extended abstract. So you'll have enough time, even if you start from now. So that's 1 month. And also, we have a great lineup of speakers for the workshop. They are all the experts on multi-agent systems, and they have been working on deploying learning approaches and generative AI techniques into the multi-agent systems. And as Professor Angela mentioned, Dr. Siqi Zhou will also be one speaker in this workshop. Okay, so if you want to know more about the workshop, feel free to check out this web page. And actually, I hope to see many of the audience in the workshop. Okay, I think I will hand over the stage to Amy again. Let me stop sharing.
Okay. Thank you very much, professors. Thank you. And it's really wonderful sharing. Thank you. And basically, that's all for today. And thank you, all the audience. Thank you for joining us tonight. And if you found today's discussion engaging, you'll be excited to learn about several IROS 2025 events that NoCope is sponsoring. There are 3 workshops and 1 competition closely related to today's topic at IROS 2025. And each exploring key aspects of multi-agent systems and intelligent autonomy. For more information, you can visit the official websites of these events, showing on the screen right now. And to stay updated on our future events like IROS 2025, please follow us on LinkedIn, or you can follow our WeChat official account for reviewers in China. Thank you for joining us, everyone, and see you next time. Thank you.
Thank you. Thank you for organizing. Bye.
Thank you.
Thanks. Bye.
Thank you, professors. Bye.
Bye.
Bye-bye.